No, they said they bring a microphone just in case. So, this today's session is actually titled Distributed Intelligence. So I co-organized this together with Christian, who is hiding in the back. So this morning I will bring the intro talk around 40-45 minutes or so, and then followed by Boris, who is here, 10 minutes, and then we go into the topic because we go also to the practical part. So what is this distributed intelligence and the computing continuum? Let me start with what is the computing continuum. The computing continuum is a fabric of all computational tiers that we currently have, such as IoT sensor networks, edge computing domain, fog computing domain like RANs, telco providers, and the cloud. In the future, possibly also if Frank figures out how to connect quantum computing, we can welcome quantum as well. But currently we have a challenge of getting the data in and out. But that's a different topic. So why is it important? Because currently the applications like e-health, autonomous vehicles, smart cities, and what have you, they utilize these different components of the computing continuum, but they just don't see it as one abstraction. Typically, they focus everything on the cloud, as we will discover this later as well. So there is a centralized and a very limited visibility over the whole system as it stands. So quality of service, quality of data, performance, everything is basically depending on this, but we have only a limited view over this.
Radio.
So,
Radio.
Which one was better?
What do you prefer?
Beginning of the party.
Okay. So the computing continuum has two interesting properties. One is that it is multi-proprietary. This means that all the system issues propagate meaning that the stakeholders that are involved in such a setting have their own interests, and they have local requirements on the infrastructure as well. So when you think about, can we have tools to better understand what is the relationship between these requirements reflected in service level objectives and how the propagation unfolds? This is kind of tricky to better understand, because typically everybody is only thinking about his own part of the infrastructure, which he owns, and not the bigger picture. The second challenge is that it is geographically distributed. This means that the challenges on deployment, service adaptation, governance, they are all spread on the geography. So what I claim here is that we need a intelligence, therefore the name distributed intelligence, in order to govern this infrastructure across the continuum. So the computing continuum is basically a substrate of device, sensors, edge, fog, and cloud, and as an abstraction able to shift the workloads across these different tiers, more or less seamlessly. That's the idea. The service level objectives as a well-known construct must hold across all of these despite the non-stationary and adversarial perturbations that we have. So the problem is who decides what runs where and on what, based on which signal and how often and things like this, right? So we can see that we can have only one continuum, but one SLO only as well. So it should not be spread all over the place. So we came up with this idea of deep SLOs, deep indicating that there is a compositional aspect to it, a hierarchical aspect to these service level objectives,
which can see the service level objectives in a decomposable hierarchical manner, binding different concepts like latency, throughput, accuracy, and resource usage together. Everything that can be measured on a hardware can be expressed in a service level objectives. So the agents that are implemented then, they see the whole contract. Sorry, they never see the whole contract, but they see only the Markov blanket, which I will explain in a short while. So in other words, we create a construct that is helpful in order to be able to do this. So a small recap of why these reactive thresholds control fail that we typically have now is because the typical state of the art presumes that it is stationary and we have centralized observability. This means that we have control over everything that is going on. But we have also non-stationary workloads. This means that not everything is fixed on a particular place. We have drifting topologies. This means that the nodes can come and go, more or less, whenever they want to, depending on technical or non-technical issues. And we have bounded adversarial perturbations. This means that we can have packet loss, different spikes, etc. Everything that can go wrong is an issue here. And the reactive controllers that are typically in place now, they lack any predictive signal. They only notice the violations after they occurred. So what we need is a predictive distributed adaptive control where we can basically understand, is the model matching the reality or not? This is the key issue here. So when we look at intelligence in the compute continuum, we can summarize and say that these distributed applications that we have, which go across sensors, edge, fog, and cloud, they fail typically when everything is with the current state of the art, only reactive and centralized, centrally managed. We need to have a predictive regulation over the reactive as well. So when we speak of predictions, I always use a biological lens, which I want to introduce to you. Some of you may be familiar with this. So when you look at the human body, for example, you see that the human body has two forces. One is homeostasis, meaning the reactive force, and one is allostasis, which is the predictive force. And we are governed by a principle which is called the free energy principle. This is a mechanism that we minimize the prediction error. And this is the idea that I bring to the systems as well. I will talk about this in more detail as we go along. And the analogy would be, in this case, that the components should also anticipate and learn the workloads that they have.
So what's the fundamental difference to organic computing, the old stuff?
I know the German guy.
Or not in industry.
Hartmut.
No, in the industry they also build this not only organic, but what's the other name? Huh?
No, Osmotic is from myself. Yes, no, that's different. I don't know exactly. This is first. I'm not sure, to be honest. It's very long ago. It was more than 20 years ago when I looked, but it was not so clearly formulated as this is. Similar ideas also exist in physics when they talk about fluctuation dissipation theory, and mainly with the idea of equilibrium and the idea of alignment. But in principle, the idea is always the same. You want to departure from the so-called signal non-equilibrium dynamics. The idea there is that you want to have the predictive equilibrium, meaning that you have an alignment between the prediction and the observed outcome, right? This is always the best case when your prediction actually is true. And this is what a famous economist, Nassim Taleb, maybe some of you know him, he wrote the book Antifragility, which builds the basis for antifragility. So when he speaks about antifragility, he speaks about systems which which becomes stronger under stress. So this is similar to muscle training, for example. When you build your muscle, what you do is that you break your muscle. By breaking the muscle, you trigger the mechanism of renewal, and this renewal leads to stronger muscles. So in other words, the muscle is an anti-fragile organ. So the question is now, is it possible to actually use that analogy also for the world of systems, to build a system which can learn from the workloads across time and become anti-fragile? Now, so this is a new idea in a sense, because anti-fragility is not typically what we aim for. We are usually happy when systems are robust or they are resilient, but anti-fragility would be taking it to the next level. Yeah, this is what I just said. So basically, how does it relate to the other notions that are very well known? Robustness is basically looking at the bounds, resilience at the set point, and anti-fragility looking at a structural improvement. So how could that look in an architecture, for example, in a computing continuum? So you could think of local Bayesian networks, for example, at the edge nodes, which predict the responses. You can have fog nodes, which have perturbation campaigns and compute the divergence. You can have cloud meta-controllers, which aggregate the signals, and then the whole system can balance exploration versus exploitation. That is one possible, thinkable approach how you could address this. Some fundamental ideas about how we work. One is Bayes' theorem. I suppose everybody is familiar with Bayes' theorem. It's basically about the priors and belief update in any network, which is quite fundamental. It's very simple, in fact. So you have some belief before seeing a data. That is called prior. Then you have a probability, a likelihood of an observation arising from a particular state. Then you have the evidence that is used as a normalizing constant, and then you have a posterior, meaning that you update your belief after that observation. So as a concrete example, rain and wet grass, right? So you have the prior that there's a 30% chance of rain, and usually when it rains, the grass is wet with 90% probability, but it might also be that somebody was sprinkling the grass, so you have to count that in as well. So when you see that the grass is wet, you have to update your belief. So this is basically what we do all the time internally, right? Now, the famous neuroscientist Carl Friston came up with a framework theory. It's theory and practice actually, but let's call it theory for the time being, called active inference. And the idea of active inference is to understand how humans learn and optimize. And I discovered it by more or less by coincidence, because he also uses Markov blankets, which I will explain in a minute. But the idea first I want to tell you is why it is so relevant and interesting here. Because active inference is about learning, about how humans learn, and it's quite different, as you can imagine, from machine learning. Machine learning, if you think about it, is actually more about machine teaching, because you take the data, you feed it into and then patterns are being recognized. So this is, you teach the machine to look into the patterns. Huge amounts of data are necessary, but when you look at how humans learn, this is quite different. Humans learn with basically one shot. So if you look at the baby, you say, okay, this is a cat. The child learns this is a cat. But if you look at machine learning, in many cases, they learn that they still might confuse, the machine learning models might still confuse a cookie with the actual picture of a cat, right? This is well known. So how does it work? So active inference is a three-piece concept, and it has the name active in it, which is very important, which you don't have in traditional machine learning. Because in machine learning, you assume you take the data and you learn something, or in brackets, you teach something, right? But it's not active in that sense. And when you see what this active inference does, you will understand the core difference. So the first idea is that the system maintains the state and make predictions about the environment to minimize the free energy. Because we as humans, we are constantly trying to minimize the free energy that we have. So the objective is, so the free energy is a measurement of uncertainty in order to maintain homeostasis and predict any change. You remember allostasis, homeostasis. So the core concepts are this free energy. So we try to minimize the difference between prediction and actual input. The second one is Bayesian inference. So we use probabilistic models to update our beliefs about the state of the world. And the third one, quite important, is also that we update our generative model constantly and use use that to generate predictions about sensor inputs and outcomes. And this is quite important because whenever we get new data, we make new observations, we integrate that into our generative model, into our worldview, we can say, right? This is from the small to the very big. So now you all have a generative model. When you walk out the door, what is it that you can expect? However, if you open the door and suddenly you're in the middle of the Alps, you have to change your worldview. Something seriously went wrong, right? And this is also an interesting property of humans that we constantly integrate into our worldview. If you don't do that, we also have that in humans. This is called stubbornness, right? You refuse to accept reality as it is, right? So we see that quite often in politics. So the mechanisms are three mechanisms. One is the perception. So that involves this belief update mechanism. Second is action. That's quite important. That's why active inference is also very much used in and looked at from the robotics perspective, because you take action in the world. So the environment is actually also being acted upon. So you see, but you also act on in the environment. And the third one is the learning aspect. So you adjust constantly the parameters of your generative models in order to improve the future predictions and actions. So this integration of these perception, action, and learning in order to create these generative models is extremely powerful. And because it's a principled approach, it's also attacked a lot by other outside people, not in the neuroscience. And I believe we are the first ones who actually try to bring it into computer science or into the systems world. So let's look at the theoretical foundations, the principles. What is this free energy principle all about? Let's look into the details. So the first one is the so-called variational free energy. This measures how well is an approximate posterior matching the true posterior. This is quite important, right? So in order to understand the mismatch. The second term is called expected free energy, which is extending this idea of the free energy to future outcomes. So foreseeing doing an action and seeing what would be the future outcome of my action. So this is also an interesting property, showing the active part in active inference. Because whenever we take an action, we simulate the outcome of that action in our own mind, right? This is quite important, and this is quite different to traditional machine learning too. Another interesting concept is the KL divergence, which measures the dissimilarity between two probability distributions, right? So if it's 0, it means it's a perfect match. Everything is as predicted, as seen, and that's the thing that we would like to have. And we can use that as a warning, but also as a learning signal. So I want to make this analogy to the human body, because if you remember nothing but this thing, I want to implant in your thinking at least. So the human body as an analogy of a complex system. The human body is very complex because it has many subsystems which have been studied extensively. So we have the skeletal system, the nervous system, the cardiovascular system, and together these three systems, they constitute the infrastructure system of the human body. We have more. We have the lymphatic, the endocrine system, which are necessary for our regulation. The nervous system with the brain has 86 billion neurons. So we can say that the brain is a computational entity, right? And this has been at the core of computer science since the very beginning. Everything that we do has the analogy to the brain. However, there is more. We also have the cardiovascular system with the heart at its center, and something that most people are not aware, that the heart is also a computational entity. It has 40,000 neurons. It's quite remarkable. So this is the second computational center. And there is even a third computational center to illustrate. I don't have it here, but it's the gut. The gut has 100 million neurons. So we have three computational centers. So when we say, I have a gut feeling, we literally mean it, right? Because we can sense it. This is the sensing part. So sensing is not only with the eyes and the ears, etc., but it's even also with the gut. So we have three computational centers in the human body. And now I bring this analogy why I do this exercise. It's because my argument is we have edge, fog, and cloud. Similarly, we should make use of these parts of the infrastructure, like the human body, and not just use one only. Why? Well, my argument is, even for a very complex system that we see in the body, evolution has created it as such that the brain is not controlling our breathing, which is quite important. Why? Because if the brain would control the breathing, maybe we would forget to breathe, and that would be the end of evolution. You read an interesting paper, and then suddenly you forget to breathe. So, it is important to understand that several things are being delegated to different layers. In the body it is the case, and this is why we can make so much progress. And this is at the same time also one reason why it is so difficult to truly understand the body and its complexity. Because in essence it is one thing, but composed of many. And if you just look at the one particular thing, you don't get the whole picture. So importantly, you have to look at the pathways which go across also from in the human body as well, if you want to fix the human body, so to speak. Now this is an interesting observation, I think. So this is medically true, what I'm saying here. The question is, does it make sense to actually transport this analogy also to the world of information systems? This is the true thing. Or should we, the true question, or should we just be happy when we can just build robust and resilient systems? There's of course more. We have the lymphatic system, the endocrine system with security, so to speak, the security system of the human body. But I don't have time to discuss all of these different aspects. So I will focus only on the deep SLO part, which is constituting the infrastructure of, but there is also of course more part regarding the learning, the collaborative aspects of this learning, and the representation learning, and the security aspects. So when we look into this analogy to the human body, we can see that the human body self-regulates. This is also a goal when you want to build anti-fragile systems. So self-regulation expresses itself in a couple of different mechanisms. One is, for example, temperature. We sweat, or we you know, in order to cool down. We have blood pressure high, blood pressure low. But actually, if you look deeply, you will see that none of the medicine actually heals the body. None. It only puts some values up and some values down. But the healing is always done inside the body itself. And the greatest mystery is always, how does this healing actually happen? We don't know, right? So what can we learn from this? We can learn from this that there is in the body basically just the top to bottom sensing. We are not able to deeply inspect what is going on inside our body. So we have just an abstraction, a high level abstraction. Like, I feel dizzy, I have fever, I have a high blood pressure, these things I can measure. But you are not able to say, okay, today I don't feel great because my liver filtration rate or kidney filtration rate is not functioning properly. You have no access to that. It's kind of an abstracted away from it, right? So when we thought about this principles, the first thing, like around 15 years ago, I started to work is, but what are the principles that actually help us to build such a system in general? And one of the first things that I spoke about was the principle of elasticity. When I speak about elasticity as a fundamental mechanism to build resilience into the systems. So we know elasticity from different fields in natural sciences. In material science, it is the property that the material stretches when you put force, and it goes back to its initial form when you leave out the stress, right? This is quite important. And this has become very important, an important lesson for cloud computing. People speaking about elasticity in cloud computing all these years. But mostly, it was about scalability, in my view. Maybe Frank doesn't agree, but most of the perspectives on elasticity are centered around the question of resources. But I would argue always that there are two other dimensions which are important and relevant to look at it at the same time. Namely, the quality aspect, so the quality is elastic, the quality of the data input and output, for example, and also the cost. So what is interesting about elasticity and why it is more than just scalability is that you look at this three-dimensional space at the same time. So you look at resource, quality, and cost at the same time. And we are all, as a collective, operating in this three-dimensional space. And this was not always the case. When I started to study, and many of you, we were not concerned about quality of data and the costs at the same time with resource consumption. But nowadays, this is becoming standard. But the way that we build the systems, considering this three-dimensional space, is not standard and has not evolved according to this principle. So if we abstract, basically we say, we want to create an equilibrium between resource quality and cost so that we don't look like this ship, so we can have an operational equilibrium of the overall system, so where we don't tilt towards one side. Either we use too many resources, or we are too expensive, or we have crappy quality of data, etc., right? So when you abstract away from that, we can say, we can look at it as a blanket, as a Cartesian blanket. We have these service level objectives operating as a threshold inside this hexahedron, and all the configurations represented by these points in this hexahedron show me what are valid infrastructure configurations, so that basically we can have a visualized blanket. So now I'm just visualizing this idea, that you can see that if the system is inside this blanket, then the system is in equilibrium.
What defines the cube?
Hmm?
What defines the cube?
The,
This hexagon, yeah.
the
hexagon.
Blank.
The configuration is defined by the service level objectives that you want to have. And on this axis of resources, cost and quality,
I have
you,
the minimum, I see.
yes, yeah.
Thank you.
So that is the basic idea. Now, when we look at the current state and you look into the question of, okay, finally this is about distributed intelligence, so we have to look into AI as well. Why is it that the current AI is not really autonomous and cannot be autonomous? Here are some thoughts. The first one is that the systems today are reactive and not proactive. So in other words, they miss this active part that I was indicating in the beginning about active inference. So they are just passive mostly. And they rely on pre-trained pattern matching without an internal generative model. So the equivalent would be that you basically educate a child, you say this is the worldview, this is the data, you indoctrinate basically, and everything else is out of question. We call that typically fanatic, right? So they predict, but they do not understand the causal relationships. Causality is at the key of everything that we look at right now. So can we build in causality? Translated into more modern terms, that will be explainable. But how can you bring in explainability afterwards, after the fact? Hard to do. You cannot. That's my argument. So you have to build in causality as a first-class citizen already. This is one of the biggest challenges, why people will not really like what I'm saying, right? Because ultimately this also would lead to a new way how we design systems. The second point is that we don't have a self-diagnosis capability. This means that we are not, when the performance, for example, degrades, maybe because of an environmental drift, there is no causal mechanism to distinguish, is there a sensor noise or is it a model failure? Is something from the model perspective going wrong? And the third one is that we typically have only fragmented optimization objectives. So there is no unified purpose. So this is also one of the hints why it is fundamentally different from reinforcement learning, because reinforcement learning has multiple objective functions, whereas active inference looks at one unified purpose. And this is also quite important as a differentiating factor for the whole edge, fog and cloud story, because if the footprint is very small, and Boris will talk about this later on as well, you are able to do much more learning also on smaller devices. So not everything is bound to a higher computational power. So the first important connecting point why I actually found out about active inference was that active inference also uses Markov blankets as a fundamental principle. This is how I discovered. Otherwise, I would have not discovered possibly what is active inference. So I was working on this topic, and I discovered these Markov blankets that they can be very useful for expressing what I'm trying to say here. So in Bayesian networks, this is a concept from Judea Pearl. In Bayesian networks, a Markov blanket of this random variable n is a subset of nodes that provide just enough information to statistically infer the value. So in this case, the Markov blanket of n is composed of the parents p, the children c, and the co-parents of the children s. And when I saw this, I was struck by its simplicity, but also the beauty, because it can actually help us to understand causal filtering.
What is the co-parent in each one?
It has been defined by...
Okay.
So basically, the idea is that we use this concept of the Markov blanket to say something and learn something about the causal relationships of the nodes which are involved here. Pearl goes on and makes different interpretations of this. He calls it the 3 rungs of a ladder of causation: observational, interventional, and counterfactual, in order to explain causality, which is quite remarkable. So what we did is basically we said, okay, these SLOs are actually like the end in the definition of Markov blankets. Let me go here to give the illustration. So the service level objective A, for example, can be constructed in a way that it shows the explicit relationship between to the other SLOs. So you can have high-level SLOs, lower-level SLOs. You can think of it as business SLOs and low-level engineering SLOs. So what is an SLO? An SLO is nothing else than a description, equation, if you like, a description of the relationship of metrics. You can measure certain things like throughput, latency, CPU usage, what have you. Anything that can be measured in the computer can serve as an input to the SLO. You can define that. Of course, as engineers, you tend to go into the lower level SLOs, right? You say something, okay, about the latency, it should be this or that, and you should not use more resources in this server than this or that, right? But if you think about a business person, the business person might go on a higher level of abstraction. But now the beauty of this concept is that you can actually link the business SLOs to the lower level SLOs like in this picture. And this can serve then as a foundation for causal relationships about what happens, for example, if I would need to reduce energy consumption by 30%. Then this is not just a heuristic that you can say, okay, maybe this is the implication. You can actually say much more about what is the causal relationship between something. And in order to do that, we bring in our old friend, the elasticity idea, which is also true for neuroscience. In neuroscience, it is called plasticity. Elasticity equals plasticity, meaning that the topology of the brain always changes when you learn something new. I repeat, the topology of the brain changes when you learn something new. This is very important, right? So now, SLOs cannot always be fulfilled, this is clear, but there is maybe an elasticity strategy that we can plug in. We can say, like in this case, SLO2 cannot be fulfilled. Okay, what can you do in order to mitigate this fact? You can intervene and you can introduce a description of an elasticity strategy, which could look like, in this case, you would need to add more resources. Or nowadays you would say, you buy new tokens, right? Or you need a higher resolution in the quality of your data. If you look at satellite computing, you would say, I need a higher resolution of the data that you are taking as from the satellite, otherwise I cannot move forward in my workflow. Like the satellite examples are very important because they require certain quality of the data, otherwise it's useless to go to the next step. So in any case, this vertical relationship is basically a proxy for causal relationships of how these SLOs are related with each other. So this can be a very powerful construct. So, and the reason why I was saying that this can be quite controversial is because if you think about it, when we design a system, this would also require us to have a novel way how to design our systems, like SLO first, which is not very popular. Now these Markov blankets are a construct which I discovered later is everywhere. And this was quite shocking to me because these causal models are everywhere in nature, from the small cells to bigger organisms, to plants, to societies, to organizations, to everywhere. Everything that we do is governed by Markov blankets. family is also a Markov blanket, you can say. So if you look at the child, you can say something about the parents and vice versa, right? The further away you go, the lesser causal is the relationship, right? And this is very important for everything that we do here. So we have done a lot of work, and Boris is the GOAT here. He will present a lot of the stuff that we have done about some initial studies, about building these active inference studies in agents in distributed systems, looking at it from the perspective of the equilibrium in this compute continuum, and what are the relationships. So a final word to my part, how we want to use this active inference now in the more modern AI architectures. So we look at active inference as a meta-intelligence. So because people always ask me, okay, how is this related to large language models? And the answer is, this is how it is related to large language models. So large language models, as you are all aware, they are governed by a lot of hallucinations, per definition. You cannot get rid of the hallucinations. But what you can do is you can introduce a higher level meta-intelligence, which kind of creates the harness for this. Okay? And this is done by the principles of active inference. That's the general idea. But I don't go into the details here because this is more what we do outside. And how we create this autonomous learning loop is by these 5 steps. We detect the anomaly via the free energy, because the meta-intelligence agent is constantly searching for the free energy in the overall system. Then as a second step, we take an epistemic action. This is the technical term that is used in active inference, meaning that I have a triggering point for data acquisition. This is the active part. I say, okay, here I do need more data. So this is also what we do all the time. When we encounter something and it is not fitting to our worldview, we say, hang on, is that real? Is this an optical illusion? Show me the data, right? At least I hope we do. Many people gave up on this as well. The third step is that we update our model. So this is our belief update mechanism that we constantly have. And then we have an active state update over the air, for example. This is, of course, relevant for machines, not so much for us humans. We do that internally, and then we monitor our convergence. In other words, are we congruent? Is my worldview congruent with what I'm doing and thinking? Or am I constantly in this battle between what I see and what I do as a mismatch? So I talked about initially also why active inference and not reinforcement learning. And just to give a brief summary here, I think you can also have this slide so you can look it up. I don't want to spend too much time because Boris is waiting here. For the next step is, as I was indicating before, I think the most important part is that active inference is a principled approach. It's not just like taking the data and feeding it into a model and that's it. It's an active approach, a principled approach, which is not just heuristics. So it is learning as we speak. And therefore, the footprint is also completely different. So it is smaller. You can also involve the edge computing infrastructure. And it has a unified mechanism for optimization, per definition, in contrast to reinforcement learning. So with that, I thank you very much for your attention for the first part. And now we go to the second part with Boris.
Hello. All right. Thank you a lot, Schahram, for this first part. very briefly, who am I? I'm Boris. I used to be a PhD student with Schahram in Vienna. Then I finished last year. Then I was, let's say, 9 months also at UPF, where Schahram holds a double position with, and I was with Victor Casamayor there, also postdoc now for 9 months. And I came back just in time to give a very nice keynote here in Crete. And, not keynote, I'm sorry, just a tutorial. And in any case, so what did I prepare to do for you today here? Is that first of all, I will very quickly go again into some theoretical parts. Given what Schahram already said so far, I think I can keep this rather short. Then the second part is that I will have also look at a little bit of high-level architecture of how we can solve basically our motivational use case. Hello. Then we have the coffee break, very quickly, so short theoretical part, then the coffee break. Then I will actually show you a little bit of the codes also for coherent notebooks. Why do I say coherent? Because they very much map this organizational cycle that we said in order to monitor, analyze, etc. And I will also show a demo app and an animation for this. And the things I would love to show you a lot of stuff, but I tried to keep it as a smaller, more cohesive part. Then also looking into future extensions of this work, potentially. So I will start with a very, very simple example. Some of you might remember this game from a couple of years ago. It was called Flappy Birds. And the objective was basically to not bump into these pipes. The only thing that you could do basically was tap on the screen, and then the bird would fly up and down. Quite simple. You only have one action basically, which is similar to also what Schahram said before. Like basically, if you have a system, you can just give it more or less resources. Basically, you can also just jump up and down and basically adhere to certain workload patterns that you might find in an environment. The problem is, how do you pass this obstacle? All of a sudden you find this, and well, the quite naive answer here is we use another dimension in this case. So if you remember, for example, this Cartesian blanket that Schahram just talked before, we had, for example, dimensions of resources, and we can also, in order to improve the reactivity of our application, we can move to other dimensions basically. So in this case, for example, we can go into other dimensions to improve the action space and therefore the flexibility of our applications. Enough about Flappy Birds, but very generally what we usually want to achieve in our applications is that we have certain requirements. Schahram called it service level objectives, and very generally it could be that, for example, for an application you want to ensure that the latency is short. When you access a submission page, you want to ensure that the energy use is low, because of course somebody has to pay the bill at the end of the day. So therefore you have lots of requirements generally. And the way in which we implement this in a system, or in how we achieve these requirements, is usually, as Schahram called it, elasticity. So this means that, for example, if you have a certain workload pattern, for example, during submission time, when a lot of people want to access EasyChair, or when a lot of students access a page, or if, for example, during rush hours, you have a lot of traffic generally. During this time, traffic peaks. And the way in which you solve it generally is by, for example, just providing additional resources. So this is, in this case, one dimension, giving more resources, giving less resource. So you can adjust basically the application according to the current demand. Problem is, this works perfectly if you have this huge server rack at home, and you can say, okay, in case I have more requests, I can just take one of these machines, take some of the virtualized resources, and allocate it to my application. Works perfectly. Problem is, what do you do if you have a beautiful edge device like this here, an NVIDIA Jetson? The problem is here, all of a sudden, you're not flexible anymore, because the only thing that you used to basically adjust in your system is giving it more or less resources. Therefore, all of a sudden, alternative dimensions become interesting. We heard, for example, from Schahram, adjusting the quality, adjusting the cost, adjusting different things about a system, and therefore, basically this motivates also why we should look into different actions that you can take within a system. And my personal belief is that this was just a general recipe for very long, just because it was very convenient. Just application isn't performing as you want, just give it more resources basically. But as we move to, let's say, computing continuum, more distributed, decentralized architectures, this doesn't work anymore as it used to be. So therefore, the tutorial that I prepared for you today is I will quickly focus on 2 research questions, which is first of all, how can you ensure server's performance when you have finite resources, so for example on your laptop, 2 laptops, but you don't have a virtual data center behind you. The second question that I want to address here is basically about the robust decision making. So this means that as the environment changes, as distribution shifts, how can you have an agent that adjusts over time? In our architecture that I will show you, I will basically split all of this methodology into 2 parts. The first part is basically the infrastructure part, if you may, which basically gives you the interfaces. So it allows you to interact with the services, observe what is currently going on. So this is what Schahram said, is basically perceiving what's going on and acting on it. The whole reasoning part is basically the second step here. So you could say, for example, you have interfaces, and you yourself, you build an agent, any sort of decision logic that can connect to these interfaces, observe what is currently going on, and send corrective actions to this. And the way in which I will present this to you is basically through 4 tutorial notebooks, where they're quite short, don't worry, but basically where you will see that how an agent can gradually learn how to optimize processing services, and also how multiple elasticity dimensions, so dimensions means having more strategies available, how having a bigger action space basically can improve the application performance, in particular when you have high load and very few resources. Okay, so the high-level simple view, as you would see it here, is that you would have an edge device, such as this NVIDIA Jetson, and you're running a couple of processing services there. So this could be, for example, you say you have an image stream and you're currently trying to collect, to detect QR codes that are represented there. Quite simple case, you have a couple of the services, you deploy them locally on your laptop, on an edge device, wherever you want. Now, as you remember, usually when we have especially such real-time applications, you have a lot of requirements that you want to ensure. For example, you want to ensure that the latency is in a certain range, that the quality is, for example, high enough, the throughput is good enough. And usually the way in which we evaluate this is just by looking into the metrics. And through some magic, you will see this magic later, we will then actually be able to infer actions that allow you to adjust the service. And basically adjusting the service means that you can take certain elastic configurations. If you remember, the traditional resource-based approach would be that you just adjust the resources. So this would mean you give it more CPU power, more RAM. But let's see, the additional dimensions that we have in our applications is that you can have a bigger configuration space, which also allow you to adjust the quality. So for example, the resolution of the images that you fit inside, the size of the model that you're using, and all of this you can adjust continuously. And in this case, this means what you propagate basically back is a couple of parameter assignments. And why we call it multidimensional is, if you remember, you had this Flappy Bird which could only improve, let's say, the resources basically. In this case, you would have multiple ways in which you can adjust a service. The 3 use cases that I'm also using in my applications, so I very much like stream processing, video processing in particular. I'm a little bit carried away by images, so I like it when something is flashing, when I can see the results directly, and I just find it interesting in general. So for example, the 3 applications that you will see is that, for example, what we run on an edge device is that we have video processing, for example, where you want to detect objects in a traffic junction, like cars or other traffic lights. What you can also have, for example, is you want to draw a mobile map around the autonomous vehicle, where you collect data through point clouds, through a LiDAR, or as we had before, the QR code scanner. That's actually quite an interesting example, because if you have 2 cars, let's say small vehicles, and you want one to follow the next, the easiest way is just by scanning the QR code on the back all the time to identify it and then build a trajectory, for example. So these are 3 very simple examples of stream processing scenarios that you could put on an edge device, on a single one. And then you might face situations where you don't have sufficient resources. And with this, I will just quickly put the QR code here. So for those of you who are interested to access these 4 notebooks, you can open this link, or let's say basically type the URL. We will now have the coffee break, but in any case, I will then later go through his notebooks, and basically the workflow, as we will have, is by following this. Some of you might know it, it's this traditional MAPE-K cycle for adaptive systems, where you start to monitor a system. So for example, you monitor how the service is going, you extract some metrics, then basically you analyze it. In our case, we do it through regression models, then we plan corrective actions, and then we execute it basically and throw it back. And with this, yeah, I will just leave the other slide basically. Okay, good. See you soon.
Thank you.